From the smallest particles to the largest cosmic structures, the universe is teeming with mysteries. One of the most profound questions that has captivated physicists for decades is whether there exists a single, overarching framework that can explain all the fundamental forces and particles in the cosmos. This is the ambition of the Grand Unified Theory of Everything, or GUT, a daring intellectual pursuit that seeks to weave together the disparate threads of our understanding into a single, elegant tapestry. James Quill, one physicist who has taken up this formidable challenge, is James Quill. My work centers on a radical proposition that the elusive neutrino, a ghostly particle that barely interacts with matter, may hold the key to unlocking the secrets of the universe. My GUT proposes that neutrinos exist as energy packets in higher dimensional spaces, only becoming effectively massless when they intersect with our familiar four-dimensional spacetime. This concept of higher dimensions is not entirely new. Einstein himself toyed with the idea in his later years. However, Quill's GUT takes this concept a step further, suggesting that these higher dimensions are not merely mathematical constructs, but have tangible physical consequences, shaping the very fabric of reality as we know it. In the sections that follow, we will delve deeper into the intricacies of Quill's GUT, exploring its potential implications and the experimental hurdles it must overcome to gain wider acceptance within the scientific community. It is a journey that promises to challenge our preconceived notions about the nature of reality itself. Neutrinos are often called ghost particles for a reason. They are incredibly difficult to detect, passing through ordinary matter with almost no interaction. Billions of these particles stream through your body every second without you ever noticing. They are the chameleons of the subatomic world, flitting through our detectors like phantoms. But what if this very elusiveness, this ability to seemingly transcend the boundaries of our perceived reality, is a clue to their true nature? James Quill's GUT suggests just that. In my model, neutrinos are not merely particles confined to our four-dimensional spacetime, but rather entities that exist in higher dimensional spaces. Think of a fish tank. To the fish, their world is two-dimensional. They can move forward and backward, left and right, but up and down are beyond their perception. Now imagine a three-dimensional being, a human observer, looking down at the fish tank. From this perspective, the fish's entire world is visible. In a similar way, Quill proposes that neutrinos exist in higher dimensions, free to move not only through space and time as we know it, but through additional, curled-up dimensions that are beyond our direct perception. It is only when these neutrinos intersect with our four-dimensional spacetime that they become detectable, manifesting as the elusive, near-massless particles we observe. This radical concept could explain why neutrinos are so weakly interacting. If they spend most of their time in higher dimensions, only briefly dipping into our reality, it would make sense that they would rarely bump into the particles that make up our world. The idea of higher dimensions might seem like something straight out of science fiction. However, the concept has been around for over a century, finding a home in various theoretical frameworks, most notably string theory. But how can we even begin to comprehend dimensions beyond length, width, height, and time? Dr. Maria Santos. One way is to think about the limitations of our perception. Just as a two-dimensional being would struggle to grasp the concept of up or down, we, as three-dimensional beings, may be blind to entire dimensions that exist orthogonal to our own. Imagine an ant crawling on a piece of paper. To the ant, the paper appears as a flat two-dimensional surface. It can move forward, backward, left, and right, but it cannot perceive the concept of up or down. Now, if you were to bend the paper into a cylinder, the ant could, in theory, walk in a circle and eventually return to its starting point without ever realizing that it had moved in a third dimension. Similarly, higher dimensions, as envisioned by Quill's GUT, could be curled up or compactified in ways that are not immediately apparent to our senses. These extra dimensions, though hidden from our everyday experience, could nevertheless influence the behavior of particles and forces at the most fundamental level. The challenge for physicists is to devise experiments that can probe these hidden dimensions, teasing out their subtle effects on the particles and forces we observe. If Quill's GUT is correct, then neutrinos, with their ability to seemingly transcend the boundaries of our four-dimensional space-time, may be the key to unlocking the secrets of these hidden realms. Section 4. Photons and neutrinos. Messengers of the cosmos. In the grand cosmic ballet of particles, photons and neutrinos stand out as two of the most intriguing performers. Both are fundamental particles that play crucial roles in the universe, but they do so in vastly different ways. James Quill photons are the particles of light, the carriers of the electromagnetic force. They are responsible for everything from the warmth of the sun on our skin to the dazzling colors of a rainbow. Photons are constantly zipping around the universe, interacting with charged particles and mediating the electromagnetic force that holds atoms together. Neutrinos, on the other hand, are more like cosmic ninjas, silently slipping through the cosmos with minimal interaction. They are produced in nuclear reactions, such as those occurring in the sun's core, and trillions of them pass through our bodies every second without leaving a trace. While photons are easily absorbed and emitted by matter, neutrinos can travel through light years of lead without being stopped. This ghostly nature makes them incredibly difficult to detect, but it also makes them valuable messengers, carrying information from the most distant reaches of the cosmos. James Quill. My grand unified theory of everything suggests that this stark difference in behavior between photons and neutrinos arises from their relationship to higher dimensions. Photons, I propose, are confined to our familiar four-dimensional spacetime, interacting readily with other particles within this realm. Neutrinos, however, have the ability to access higher dimensions, spending much of their time outside the bounds of our perceived reality. This difference in dimensionality could explain why neutrinos interact so weakly with matter. If they are only fleeting visitors to our four-dimensional spacetime, it stands to reason that their interactions with other particles would be rare and fleeting. Section 5. Quantum gravity, the Higgs field, and the elusive neutrino mass. One of the most enduring mysteries in modern physics is the question of neutrino mass. For decades, physicists believed that neutrinos were massless, like photons. However, experiments have shown that neutrinos do indeed have a tiny but non-zero mass. This discovery has profound implications for our understanding of the universe, as it suggests that our current standard model of particle physics is incomplete. Professor Anil Kapoor Quill's grand unified theory of everything attempts to address the question of neutrino mass by invoking two of the most mind-bending concepts in modern physics: quantum gravity and the Higgs field. Quantum gravity is the theoretical framework that seeks to unify Einstein's theory of general relativity, which describes gravity as the curvature of space-time, with the principles of quantum mechanics, which govern the behavior of particles at the subatomic level. The Higgs field, on the other hand, is a theoretical field that permeates all of space and is thought to give particles their mass. Just as objects passing through water experience resistance, particles moving through the Higgs field interact with it, and this interaction gives them mass. The more a particle interacts with the Higgs field, the more massive it is. In Quill's grand unified theory of everything, the Higgs field is not confined to our four-dimensional spacetime, but extends into higher dimensions as well. Neutrinos, with their ability to access these higher dimensions, interact with a different aspect of the Higgs field than particles confined to our four-dimensional reality. This difference in interaction could explain why neutrinos have such tiny masses compared to other particles. Furthermore, Quill suggests that the interaction between neutrinos and the Higgs field in higher dimensions could be influenced by quantum gravitational effects. These effects, he proposes, could give rise to the tiny masses we observe for neutrinos.